All right, today we are going to talk about the structures and types of solids and kind of tie together what these different type of bondings mean. Now there's two big broad categories. You have crystalline solids that are very organized, amorphous that are very disorganized. This is just some examples of some common lattice structures. We're not going to get too specific, but there's all these different geometric patterns which ultimately minimize the energy. Some you have simple cubic, body-centered, face-centered, but this terminology we're not going to get into today. We're going to mostly focus on crystalline. There are some pretty important amorphous solids as well. Glass is one of them. They have this irregular formation and kind of don't follow all the rules, but they're out there, but we're going to focus on the crystallines. Okay, now with every crystalline solid, you have this lattice structure. We've talked about lattice energy, which is the energy associated with gaining this crystal structure from two gaseous atoms. And it shows the 3D arrangement of parts. It's made of small repeating parts called unit cells, and that's kind of what I was referring to in the last slide with the body-centered or simple cube and all those. X-ray diffraction is a process used to determine the structure of crystalline solids, and it's just it. They zap it with this X-ray radiation, and based on how it changes direction or is diffracted, they can use that to determine the structure. So, all right, when we classify solids, it's essentially what occupies the lattice point. Or when we were looking at those cubes, I always like to think of them as like Tinker Toys. When I say lattice point, it's that thing right there. What is the thing that is being held together by these IMFs or by these bonds? And that's where the lines are going to be either IMFs or bonds, like or intramolecular forces, like we talked about last section. Okay, ionic compounds. There are ions at every point in the lattice. Example is sodium chloride, where you have sodium ions connected to chloride ions in this repeating pattern like this. Okay, so your ions are at your points. Now, molecular solids are covalently bonded, regular molecular compounds, and these have molecules at each point in the lattice. So let's see if I can get this in. This is like water, 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 where what's holding them together here are these IMFs. Sugar would be another example where you'd have sugar molecules at each point in the lattice. Okay, atomic solids, which we have not really focused on all that much, have atoms at each lattice point. Primarily, the main ones we focus on are called metallic, and these are delocalized covalent bonding. This is also when we refer to as our sea of electrons that we're going to discuss here a little bit more. You also have atomic network or network, and these are just kind of a unique, strong covalent bond, and we'll look at some examples of these, but these is things like diamond, quartz for silicon, where you have only one type. And then also for group 8A or group 18, as we would probably call it, you have London dispersion forces, and that's going to be all our noble gases. Okay, so you just have some unique situations, and these are just this is the type, this is what's at each point, the type of atom, and then this is the force that's holding them together. Metallic bonding, strong covalent, and then London dispersion. Okay, so this is just again showing you some schematics. This is atomic network. This is diamond. Each one of these represents carbon. It's a very special example. Ionic, you've got ions, and molecular, those are water molecules. And the dots between all of those are the hydrogen bonding that's holding them together. And this chart, which is in your book, can also be found. It kind of summarizes everything, what I just said, all in one page, where you've got the bonding and you've got the lattice points. Okay, metal bonding. Metallic crystals can kind of be viewed as metal atoms or spheres packed together in the closest arrangement possible. The closest packing possible is when each sphere has 12 neighbors, where you have 6 on the same plane that completely surround it, 3 on top because they settle into the grooves, and then 3 on the bottom. Again, it's just an example to show you how these things actually start to go together, but I'm not going to ask you to explain this specifically in terms of a memorization point. But bonding of metals. The highest energy level for most metal atoms does not contain many electrons. This is where we have the whole D, 2, 3, 4, 5, D, and P blocks. And since they're all to the left of the stair step on our periodic table, they all have lower numbers of valence electrons. And so these vacant overlapping orbitals allow the outer electrons to roam freely. And this is what last year we referred to as our sea of electrons, where, if this is like a zinc, example of a zinc metal, where you have these 2+ cations, you've got these 2 extra electrons from every atom floating around. This might be an example of like a silver metal that has a 1+ charge on it, and all these electrons floating around. So just some samples there. Roaming electrons form a sea. The bonding is essentially the same in every direction. We also refer to this as being delocalized, meaning that the electrons aren't necessarily assigned to one particular atom. And one layer of atoms can slide past one another without friction. And this allows for things like malleability as well as ductility. So what's next? And conductivity. Oh, I think your slide is a little bit different here, and I don't think I had the conductivity slammed on the bottom of that last one, because I'm going to talk about it in a minute. Now, just as a reminder, malleability is the ability to be hammered into a thin sheet. Ductility, is the ability to be pulled into a thin wire, and this is what was on the bottom of that last slide. That conductivity of both heat and electricity is simply all from the freedom of electrons, more so electricity here, but freedom of the electrons to move around the atoms. And if those electrons can move, then electrical current can be passed through and we get good conductors. Now, alloys are really a mixture of elements. So we're not creating a brand new chemical, we're mixing metal elements that have metallic properties. And there's 2 types here. You've got superstitional alloy, where host metal atoms are actually replaced. This happens when they have similar sizes, where you're literally taking something out, putting something back in, and we're going to see on the next slide that steel's a good example of this, as opposed to an interstitial alloy, where smaller metal atoms will occupy spaces. So this is when the metal atoms have a big difference in size. So some common metals that we're used to: brass is substitutional, and you substitute something in, and usually about 1/3 of the copper atoms are replaced by zinc. There's a few other metals that can be used as well, but you can see that zinc takes the place and it just makes it stronger. That was a big thing with brass. Now with steel, it's interstitial. You have these iron atoms and you have lots of carbon atoms that get put in between it, and this just makes it much harder and less malleable. And if you know anything about engineering and the production of steel for construction, they can do some pretty amazing things just by taking up all the extra spaces in those elements. Okay, network atomic solids. I know these are kind of the toughest to understand because we've never really talked about them. They contain strong covalent bonds, and so like with carbon, I'm going to bring all these up so I can see my picture here, as opposed to the molecular crystals where you have an intermolecular force. This is truly, and carbon has its own, I'm not doing a very good justice here and showing you diamond, but this is actually a very strong covalent bond. It's not an intermolecular force, so it makes these network atomic solids viewed as one large molecule. They're usually very brittle because they cannot slide past one another. They're also very poor conductors because they don't have roaming electrons. All the electrons are roped in. The 2 most common examples that we see, one is graphite. And just to show you some patterns on the graphite, it's very slippery, it's black pencils, that's where we get graphite pencils from. You get these layers of fused 6-membered rings. Each carbon is bonded to 3 others, so if it's got 3 bonds on there, you're going to have, if we look at this one right here, it's got 1, 2, 3 coming off of it. 3 bonds is going to be sp2 hybridized at 120 degrees. The 2p orbital is what helps form this network of pi bonds. So you've got these free roaming pi bonds that are going to share electrons, and they're going to help pull everything together. It makes layers very, very, very stable. And there's a weak bonds between the layers, so that's why they can kind of slide past one another. So you get the pi bonding kind of between all of these guys, but that you get weak bonding between the layers, which is why we use it in pencils, because the top layer slides off and the rest of it kind of sticks together. Now diamond is a tetrahedral arrangement of carbon atoms, so you get covalent bonds made by the overlap of sp3 hybridization, and these are very, very, very stable. If you know nothing about diamonds, they last forever. But they're used in that's why they're used in drilling, whether it be the dentist or in industry. And it's just because they have these repeated overlap sp3 hybridizations. The electrons aren't moving, they're locked in, and they kind of solidify everything. Okay, then we're going to talk about molecular solids. And these are different from these contain different molecules at each lattice point. Very strong covalent bonds within the molecule, but much weaker IMFs. Okay, so this is when you've got water or sucrose at each lattice point. And as the size of the molecules increases, okay, this is different than what's on your notes, I think. So add this in there. As the size of the molecule increases, okay, the London dispersions get stronger. And essentially the London dispersion, IMFs, dipoles, all of them, okay, get stronger due to larger electron clouds that are more what we refer to as polarizable. They like that AP word. They like to ask about different reasons why things have higher melting points and higher boiling points. And as the size of the molecule increases, London dispersion will get stronger because of the larger electron clouds. It's not just the fact that they're larger molecules, so they have more mass. It's this, they're more polarizable. And when a molecule is polar, the IMFs are much stronger, dipole-dipole or hydrogen bonding, and we see the same pattern for as the size of the molecule increases, they also go up if you're just comparing like kind of along a group trend. And we'll talk more about this in class. We'll do some sample ones for responding to AP. And again, this is just showing you of atomic separations in terms of as well as intermolecular attractions for some of these materials. Okay, so distance between molecules and between the atoms and just kind of comparing that. All right, we've got ionic solids. I think this is the last one. These have very stable, very high melting points because they're held together by these very strong electrostatic forces, otherwise known as ionic bonds. Ionic and covalent bonds are the strongest. That's why ionic bonds and covalent network are have some of the highest melting and boiling points that we're going to find. Larger ions are arranged in closest packing arrangement. It's just the smaller ions will fit into the holes and they lower their energy. Now, I'm not going to ask you about these. I show them to you just so that we've seen them, but you can have the ions. Remember, these are the unit cells that are the repeating patterns that we see over and over again. You can have what's called in the center, in face where half of the ion, in the edge where it's a quarter, or 1/8. And this is just kind of showing you some of the different patterns that they can get for unit cells. So here you've got cesium chloride, here you've got sodium chloride, which you can see is just different. It's all based on lowering the energy as best they can. You've got some other options, which I don't think you have this slide, but you've got zinc sulfide, calcium fluoride, and I can't remember what this bottom one is. So, but it's just some different patterns that we see. And this table, which is on page 484, kind of summarizes all of this and puts it in one spot in terms of the type of bonding and the type of properties. This is going to be key down here because AP likes to give you, explain the difference in melting points of these substances using bonding and structure or polarity and all those things we kind of tied together. So we'll do several of these in class. We'll also do a concept map to kind of summarize all this. So